In this lesson, we're going to learn about the specific types of chemical reactions that we see and how to represent them as equations. This is the first set of slides. There'll be a second set of slides. And this first set of slides will actually go over two different types. Quick overview again here. You can take a quick look. I've listed the first, or the five here that we're going to go over. And we're going to first start off with this one at the top of the list. And it's important to recognize that, there are lots of thousands of different types of reactions that exist. But we're going to focus on the ones that are the most important and the most common, and then go from there. One of the things that we'll have to do a lot of is also write chemical equations a lot and how to represent, the reaction as an equation on paper. So this is going to be a list of steps of things that you'll have to consider, and we'll pretty much have this around all the time. So please take a look at this. I've taken these and snipped them out and then put them in other slides too, just so we have something to reference or have this to reference. So just, keep this in mind, because this is definitely something you want to always have available and help you keep track of the work that you're doing. So this, again, how we write chemical reactions, we can use this process right here to help keep track of our progress. All right, so let's go and go over the first reaction type 1. This is actually a pretty hefty one for what it's worth. And the other ones, there are some similarities, some differences, of course, but this is a nice basis to start from, and then we will see how these work in comparison. All right, this one's called double replacement / double displacement. I'll typically refer to it as double replacement, but either is interchangeable. But this essentially when you have two compounds that exchange ions and form two new compounds. So this general reaction you see right here, it's got AX and BY, and that's the yield sign, is going to form AY and BX. So the AX, right, that's going to be the positive cation A, negative anion X. B is a positive cation, Y is a negative anion, and they effectively just swap places with each other. So the positive of one combines with the negative of the other. Please do note that, of course, cations are always listed first. So that's why you see the A and the B first and the corresponding Y and X afterwards. Generally speaking, how you know a double replacement reaction is present is when there's ionic compounds that are two ionic compounds anyway, as a reactant or as reactants in solution. Also, you might see acids involved and sometimes bases too. That one's a little bit more nuanced, and we'll get to those later. But recognize again, for the most part, you're going to look for two ionic compounds. So here's a set of examples. I want you to take a look at these and tell me which one of these are going to be double replacement reactions. So based on what I just pointed out, right, we're looking for two ionic compounds as reactants. So take a look at example number 1. You got NaCO3, FeCl2, right? Those are two reactants, and they appear to have swapped with each other, right? The Na seems to be combining with the Cl, right? And then the CO3 seems to have combined with the Fe over here to form FeCO3 and NaNO3 there. So yeah, that looks like an ionic compound swap where the ions swap with each other. Therefore, yeah, I think this is going to be considered double replacement. The next one. CO2 and H2O produces C6H12O6, that's just not familiar, and 6O2. That one doesn't look like it's going to be a double replacement because it doesn't start with two ionic compounds. All right, so that's not going to be double replacement. All right, number 3, this one right here looks like two covalent compounds. All right, that already fails the test, so that's going to be a no for that one. The last one, it's got a lot of terminology here, but I think we can figure it out. A solution of sodium sulfate is stirred into a solution of strontium chloride. Well, sodium sulfate, it's a metal, and sulfate is a bunch of nonmetals. That's an ionic compound. Strontium, metal, chloride, nonmetal, that's an ionic compound. So yeah, I'd actually consider that to be a double replacement reaction. Even though you can't see the formulas, you should still be able to sort out why it's going to be a double replacement. Now is how we actually write it out. So these give you effectively how to write, or the prompt for how to write these. Now I'm going to kind of speed through this a little bit because parts of this I think you should be able to do no problem. But I think it's something that's worth practicing, especially the balancing part, and then knowing how to identify it. So here we go. A reaction between solutions of silver nitrate and sodium sulfide produces silver sulfide and aqueous sodium nitrate. To speed things along, I went ahead and wrote out all the compound formulas that are a result of this. So you need to make sure that you can do this on your own as well. I'm doing it for the sake of just kind of having it down. Let's go and fill out the rest of the information we need. We need to include the states of matter. These are all stated as solutions, so these are aqueous. This is also aqueous. This appears to be the solid, and this is aqueous. And then finally, you got to be able to balance it. So looking through this, you have to add the appropriate coefficient. I'm going to do this in green here, so that'll be a 2 right there. Oh yeah, also a 2 right there. This next one here is going to be a little bit more involved because it doesn't give us as much information. It says cobalt 2 sulfate solution is dripped onto a solution of barium chloride to produce a solid containing barium and a soluble cobalt 2 product. Now, what's different about this one is they don't give us the identities exactly of the products. They kind of just tell us that there's something we know about it, not exactly everything. So let's start off with what we do know. Let me go around the reactants here. So we got those taken care of, and now we know a little bit more. It's saying that they've got a solid containing barium and a soluble cobalt 2 product. So let's go and try the first one. We know that the barium is involved here, so let's do Ba. But what's going to be the other part? Well, remember, these are ionic compounds, and part of double replacement reactions is that they swap ions, they exchange ions. So barium, right, which is over here, that was bonded to Cl, let's actually now have it combined with SO4. So barium is going to try to combine with SO4. And when I say try, it's going to. So in this case, what compound can I make with barium and sulfate? And you got to be careful here. You can't really just write exactly what's there. And this kind of works out a little bit, but let's double check because these are ionic compounds also. We need to make sure that the charges match, right? The charges are overall neutral. So barium is a positive 2 ion. Sulfate, the polyatomic ion, is a -2 ion. So it actually works out that this is going to end up just being BaSO4. Right. Remember, I'm not writing out BaSO4 just because there's one of each on the left side. It's because, that's how barium sulfate would exist. So we have to write a legitimate compound. Now, the next one, again, writing a soluble cobalt 2 product. So there's going to be something involving cobalt 2. Right. And we know that cobalt 2 is a positive 2 ion. Right. And what's that going to combine with? Well, if you look over here, right, the cobalt, that's that. We have now going to be combined with Cl. We're going to combine with the other substance's negative ion. So let's go ahead and swap that part to make it CO, and then combine it with Cl somehow, right? So Cl is a -1 charge. We're going to make this neutral. So to make it neutral, I'm going to look at CO being just 1. Cl, we need to make that 2. So let's go ahead and double that to make it CO, Cl2. Now, I want to be clear about this, right? I didn't write down Cl2 just because there is a 2 here and a 2 here. That's a coincidence. I wrote the Cl2 because that's how cobalt with a +2 charge and a chloride with a -1 charge combine to make a neutral compound. Now, to finish it off, of course, you have to write the states of matter, so let's go ahead and do that real quick. You can see all the labels thrown in there based on the language we just saw. And let's go ahead and balance it. Well, it turns out that it's all pretty much balanced already. So at the end of the day, we got to make sure that we can clean this all up and know that the only thing we really needed to see was what is here. Like this. Come on. Come on. Let's try it one more time. Here we go. All right. Now, some other terminology we need to recognize here is that double replacement reactions they only really occur if you have at least one non-aqueous product. So one non-aqueous product means something that's not dissolved. There's a couple of examples of how we can have non-aqueous products. That includes an insoluble solid, right? A solid that is not dissolved. It's just in the liquid, but it's not actually dissolved. That's known as the precipitate. This is a term that you want to go ahead and know as well. So that precipitate is something that comes out of the solution. Gas formation can sometimes occur as well, where it bubbles out, right? So the gas is going to just leave the solution. It's not dissolved. It's in there for a moment, but then it bubbles away. Or sometimes it forms liquid water. Well, it happens from time to time. But liquid water doesn't really technically dissolve. It's not aqueous, so we don't really consider it to be aqueous. So that's considered also as a non-aqueous product. However, if you end up having a situation where both products are soluble, no reaction occurs at all. And we'll talk a little bit more about why that works out. But basically, just because you can write an equation out doesn't mean that it's going to work. It just means that you wrote down an equation. So we have to verify whether or not a reaction will occur, even if the written reaction looks like it might anyway. So let's see how this works. We have to use something called solubility rules to help us out. Now, solubility rules, this helps us know if something is soluble or not, right? Because why is this important to know? Well, remember, we have to know if a reaction occurs, and in order to know if a reaction occurs, there has to be at least one non-soluble product, right? See the previous slide for that information. So the solubility rules more or less tell us how this works. If something is insoluble or soluble, you either label it with an S or an AQ. S because that's a solid that is not dissolving. AQ because that means it is dissolved in there. Just note that the solubility rules, I'm going to pull it up. Looks like, kind of a lot of just words all jumbled together, but there's a pattern to it. And just know that you don't have to memorize these. You can if you want, but these will be available to you at all times. So generally speaking, you can see that this is broken down into two main sections. You have the soluble section, and you have the insoluble section. So it's kind of nice to know that things listed on top here are more or less things that are always dissolvable in water. And then the bottom here, you see the insoluble things. These are typically things that don't dissolve in water. They're typically solids just floating around in the liquid. But let's go and try and break this down a little bit. If you look at the language here, for example, number 1, all compounds containing alkali metals and alkali metal cations technically, and the ammonium ion are soluble. So anything that has those substances, they're going to be dissolvable in water. For example, right, let's say I have something like K2S, right, side example, K2S. Well, K, right, that's potassium. That's a group 1 metal. Right? That's going to be a cation from the group 1 metals. So I don't even care what this is. Like this actually, has some other rules. But the important thing is that once I know that K, right, it says that all compounds containing alkali metal, so that includes potassium, are soluble, I know that this is going to be soluble. So if I ever see this, I would write this down with the AQ symbol. That's a pretty terrible AQ. Right. On the other hand, if I look down here, it says all hydroxides, for example, are insoluble except those containing the alkali metals and these specific things. So what about, let's say, I don't know, what about iron hydroxide? Fe, I'm just going to make this up, iron hydroxide, right? So if I look for iron on this page, I'm not going to see it anywhere. Iron itself doesn't really have any specific rule, but the hydroxide part does, right? So the OH part does. So hydroxides are considered insoluble except those that contain yada, yada, yada. So in this case, the Fe, right, these are not any of these exceptions that are listed here as something. So this would be considered insoluble, right? All hydroxides are insoluble. So in this case, I'd write a little S next to it if I were looking for this. So if you go back to the slides here, so you have the solubility rules that you can apply. So now I want to just take a look at this. You guys have an option to kind of look at the various ones and give you a moment to try this out. So I'm going to pause it for just a moment. Okay, and be sure to know that you can check the answers on the notes section of the slides, but here are the answers. One thing that's important to recognize is that these, it seems like the sentence might make sense or it might be leading you one way, but then there's an exception to worry about. For example, part 5, BaSO4, right? If you look at the language, it says all sulfates are soluble. Unfortunately, many of us tend to just stop right there and pretend that the rest of the sentence doesn't exist, because if you look at it, it does say except those containing yada, 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 yada. And it turns out, in number 5, BaSO4, well, Ba is one of those examples here that shows up right there. So it turns out that is in fact, BaSO4 is in fact insoluble. So let's go ahead and try this out. You're going to have to take some time to figure these out and take a look at the reactants and then determine the balanced chemical equation. I'll do 2 of them with you, and we'll see what happens. So to start, we have these 2 as are my reactants, and then let's go ahead and figure out whether or not, or what kind of products they form. Well, it looks like Y, yttrium here, that's going to end up combining with OH, so Y, and then I have OH. I know that Y is a +1 ion, OH is a -1 anion, so that's fine the way it is. And then the other substance is going to be K combining with ClO3. So K is a +1, ClO3 is a -1. So that actually works out in terms of the charges. Let's go ahead and put some states of matter on each of these. I have aqueous reactants, so I can go ahead and assume that both of these are aqueous. And then my products, well, it didn't give me any information. But again, how do I know if these substances are solid or aqueous? Well, check the solubility rules, apply them. You'll see that YOH is in fact a solid, and then KClO3 is aqueous. Right, that's going to be something that will be dissolved. So one thing you have to do, of course, when you look at these is always look to see whether or not the solubility rules allow this reaction to occur. And in fact, yeah, this one will occur because it does form one insoluble product, ends up being YOH. This is our precipitate. Let's try the second one. And here are my 2 reactants, so I can see that I'm going to swap out Ca, and that's going to combine with CO3. I know that Na is going to combine with this guy right here, left off with 2, excuse me. And let's do a swap. So let's make sure we swap it with the appropriate method. And you can see that they have now been swapped appropriately. Please do note, for those of you who are wondering, wasn't there an Na2 here earlier, and wasn't there 2 acetates over here on the left side? Yeah, there were, but don't forget, right, we have to write compounds that match what we know are the rules for ionic compounds. And since Na is a positive 1 ion, acetate's a negative 1 ion, we only need 1 of each. We don't need to add any extra there. So don't just blindly copy stuff from the left side and assume it's right. You still have to go through the process of nomenclature. So to finish it off, let's go ahead and throw in the states of matter. If I look at my solubility rules, I'll see that CaCO3 is in fact insoluble in water, and the Na2 or NaC2H3 sodium acetate, that is going to be aqueous. I know that's going to work out. And then I'm going to go ahead and balance it by throwing a 2 in front right there. Let me use another color just to get it right there. And then that's basically it. Right. Does this reaction occur? Yes, it does, because it forms at least one insoluble product. Right, try the last one on your own, and that'll do it.